All right, so now at this point, we have seen how we can find the inverse of a function once we knew that that function will have an inverse. Okay, and so in the end, we have a function, and we have learned that a function, any function, we have a graph. So once we have a function and we found its inverse is also another function. So being a function, the inverse of a function will also have a graph. Okay, so since we recognize that a function and its inverse have some relationship, the inverse relationship, then let's now learn any specialty about the graph of the inverse function to see how it's related to the graph of the beginning function. Okay, and so let me now bring up the following example, and it's not really an example that I formally put an example number. It's just a demonstration example over here. Okay, so let's look at we want to consider, okay, there's f of x equals eight x cubed plus 1. Okay, and then its inverse is found to be cube roots of x minus 1 over 8. Or indeed, we can write it as f inverse is 1/2 cube roots of x minus 1. All right. So as a matter of fact, if you notice, this problem here came from our example 2, the last problem before the FYT. So we have a function here, f of x equals 8x cubed plus 1. And in example 2, I showed how we found this function here, 1/2 cube root of x minus 1, or we can read it as a cube root of the entire x minus 1 over 8 being the inverse of f. So now here's what I want to do. So with these two, now I have f being the function, and I have f inverse being another function. Well, these two are related because they are the inverse of each other, but in the end, that one has a graph, this one will have a graph too. Okay, f of x has a graph, f inverse will have a graph too. So let's now use a graphing device, a graphing technology, a graphing utility, okay, to graph the two functions here. These are, at this point, these are probably a little advanced function that you probably have never seen. So let's use a technology. Let's allow the technology, a graphing device, to help us instantly pull out the graphs of these two, because that's the main aim right now. We just want to see how the graphs of these two functions relate with each other, or at least any connection between the two graphs here of the two functions being on the board here. Okay. All right, so now on my graphing space here with decimals, so I, again, as you have seen throughout my many lectures already, I mostly stay with decimals as my main graphing utility right here. But outside of decimals, you are also allowed to use your standard TI calculator, the graphing calculator. Okay, so now on the graphing screen right here, let's go ahead and graph. So the idea now is that we're just simply going to graph the two functions as we're going to just graph the two functions as two separate graphs, okay? But we put them on the same graphing space so that we can start recognizing some relationship, some connection between the two graphs. So before I show the graph, how about let me set out a couple conventions. To clearly organize our work right here, I'm going to use the graph for the original function here in red, okay? And this function here, the inverse function, I'm gonna show the graph with decimals in blue. All right, that's what it is. And so now in that way, on my graphing screen right here, this is, according to Desmos, this is the graph for the function 8x cubed plus 1. Okay, and so again, it doesn't have to be any advanced. I mean, you don't need to worry about how we graph, and if in the worst case that you don't have any technology, you can easily construct your table of values. This function is obviously, as you're seeing, it's a one-to-one function, and you can just use any substitute in any value, and you get it's a simple calculation. So you can use any value to calculate the output, and then you put you represent your table of values through a graph like this. Okay, and so that's the graph for 8x cubed plus 1. And then for anybody, if you are using, for anyone that's using the TI calculator, TI 83 or 84 plus CE, like I'm having here, is doing the same functionality. So you go to y equal, okay, and now you're going to type in 8x cubed plus 1. Okay, that's your function for f of x. And as a matter of fact, as I said, I want to draw the original function in red ink and then the inverse in blue. So I have to clear this out, and I will put my original function in the y2 right here. So that's just a little bit that we have to adjust with this particular technology right here. So 8x cubed plus 1. Okay, so that's our function. Okay, so now let's show the graph using the TI calculator. That's the function. That's the graph. And so now, just like that, with Desmos, that's the graph. So the two versions looks exactly the same. Desmos is a little more precise, a little more the better resolution. All right, and so now with this line right here, now I'm going to use Desmos to instantly bring up the graph for 1/2 cube root of x minus 1, or you can also type cube root of x minus 1 all over 8. Okay. So now this is the graph of the inverse function in blue. Okay, 1/2 cube root of x minus 1. This is the function. All right, and now with the graphing calculator, with the TI calculator, 83 or 84, they're all going to work the same. Okay, so now we're going to go back to that y equal button, now with the blue graph right here. So the TI calculator is a lot more limited, and so it already had these color sets right here. So if we want our inverse to be in blue, we have to type our inverse function here. Okay. Otherwise, if we have a different color defining, then we can have our own choice on that. All right. So now I'm going to type now for anyone, and it's the same with Desmos right here. 1/2. Okay. But now to type cube roots, I'm going to go with, I'm going to do the following trick. Times, and now open parentheses, x minus 1, because it's cube root of x minus 1. So I'm going to put x minus 1 inside of a 1/3 power. That's how I'm working with cube roots. All right, so 1/2 times x minus 1 to the 1/3 power, or another way of saying this is the cube root of x minus 1. So now I'm going to hit the graph button. And now the TI calculator will show the graph in blue. This is the graph for the inverse function, f inverse. And so now this graph here with the TI calculator, unlike Desmos, the resolution is not so good. Okay, and it's not square zoom right here, and you can see it's a little bit out of scale right here. So if we want to adjust that to make it look like something similar to Desmos, because Desmos is in square scale. So the grids here are going square, so we recognize more easily the relationship between f and f inverse. But now for the TI calculator, it's a little bit out of square scale right here. So to maintain square scaling, we're gonna go to zoom right here. Okay, in your calculator, you go to zoom, okay, and then select a fifth option right here. Okay, so zoom square. And now it's in square mode right here. So now, see, this is 1 unit square, and now things are all the 1-to-1 ratio. And so now I can zoom it in a little further. Okay, and now I'm going to select option 2 right here to zoom in. And I'm going to zoom right at the center. Okay, with the TI calculator. So as we zoom in, the resolution does improve. But now, I realize with the calculator, I've zoomed a little too far. Okay. So we have to go back and zoom it out one step. All right. So that's about good enough for us. So now with this graph in decimals, so now with this graph with the graphing calculator, or with the graph in decimals here, we already saw we noticed there's some relationship between the two functions. Okay, and at this point, this is the reason why when I began introducing the concept of inverse function, I also mentioned earlier that it is highly recommended that this lesson is viewed after it's watched, after you have learned some concept about the transformations of a function. Because now, to me, when I teach about inverse function, I see it's easier to explain to the students that the graph of an inverse function is a transformation. It's also a transformation because it holds the exact same structure, the same shape. Okay, but I want to explain that as it's a transformation of the original function. So now, this is what I mean. The graph of the inverse in blue here, I want to explain to my student. I tend to explain to my students that it's a transformation from the original function in red right here. But what kind of transformation happened here? All right, so now let me put in the following line right here. This is probably the first time notice for somebody. But if I now put in a 45-degree line right through the origin, okay, so again, this is a 45-degree line right through the origin. We can do the similar thing with the TI calculator. Okay, on the TI calculator, we can go back to y equals, and the 45-degree line is famously known as the y equals x equation. And then like decimals, I use black color, so this is the right choice, the right place to place my equation. So y3 equals x. But now let's put it together. All right. So now that's my 45-degree line. It's a graph in the end. It's a graph, but I purposely put this graph here simply as a line. But then now once we place that line on, we're going to start recognizing some specialty, some special relationship between the blue and the red. Okay? And again, on that decimals version with the black line present here, we're going to start recognizing some specialty, some special relationship between the blue and the red through the 45-degree line. Okay, the 45-degree the line right here. All right, so right here, the picture is still here. What do we recognize right here? And this is the reason why I've been saying I see the graph of an inverse function as a transformation, of the original function. So what transformation did I see? It's not a vertical shift, okay? It's not a horizontal shift. It's not a scaling. It's not stretching. It's a reflection here, but it's a reflection through. Now let me bring that in full screen view right here. Okay. Now it's a reflection through the 45-degree line right here. So from where the 45-degree line, and suppose we already had our graph of the original function in red here, then we're gonna draw a 45-degree line. Okay. And once we draw the 45-degree line, we can just simply see that. If we treat the 45-degree line here as a mirror, then the blue graph, which is the graph of the inverse function, is exactly the mirror image of the red graph through this 45-degree line. All right, and so in formal math term, a mirror image like that, it's a reflection, but this time the reflection here is through the 45-degree line. So we have the graph of one function here, there's a 45-degree line, and so we draw the graph of the other function as a reflection. And that graph right there reflected through the 45-degree line is the graph of the inverse function. All right, and so in that way, since now I want to approach the graph of any inverse function as a 45-degree line of reflection, 45-degree reflection through of the beginning function, then in that way, back in my lecture when I introduced about transformation, I talked about that concept about using the guiding points, okay? And so let's bring it here. Let's bring it out right here. And because I want you to draw some usefulness about the guiding points and bring the usage of the guiding points here in this problem, because it's a transformation again. Okay, so now back in the graph, in complete full view right here. All right, one guiding point I noticed is that it has a point at 0, 1. All right, that's 1 point. We're having it, and then let's put that in red ink right there. All right, so 0, 1, that's 1 point that we're having right here. And then there's another point, and the whole idea about the special guiding point is that simply we just picked right at those points where it stays right on the grid. It seems like they stay right on the grid. So this point right here stays right on the grid. And then we notice the shape of the original graph right there. All right, now I have to zoom it out a little further. And so now at 1, 9, okay, we have another point. All right, and we have another point right on the grid and stays on the graph. So this point right here is another good point that we can use for the guiding points as a guiding points. And then I can have another one. How about -1 down to -7 right here? -1, -7, and I can zoom it in even a little further. Okay. All right. So these points right here are the guiding points that I use on my red graph here. So think about it. Now, if this point is if any of these points is being refracted, if we are trying to produce the refracted point, okay, of those points through the 45-degree line. So if this is the mirror here, then the refraction of these points through the 45-degree lines has to be the point where, so now, let's take a look at that one. If it was 1, 9, then to take the reflection, the mirror reflection through the 45 line, simply all we do is just, now let me do the magic right here. All right, so just now I popped out a point in blue right here. So let's read it. This one under the original function is 1, 9, but this point right here, and you can see that it's through the eyes right here, it's the 45-degree, it's a refraction through this 45-degree line. This point in blue is the refraction of the point in red right here through the 45-degree line. So what just now has happened to their coordinates values, to their x and y values? They switch over, they switch role. All right, so this way of my explanation, this way of how I've been explaining to my students about how we can recognize the transformation, I mean the graph of an inverse function as a transformation, with transformation in a sense that we switch the x and y right there. How is that consistent with what we have done earlier? Now in our work, as part of the steps to find the inverse function, there was a step where we interchange x and y, okay, and then we solve for y. And so that's the whole point, and that's how we are seeing that here. Part of the work to find the inverse function, we have to interchange x and y. So now when it comes to real case right here, when it comes graphically represented, okay, I mean it takes a lot more math details to prove this truth right here about why, you know, every point on the inverse graph is the exact flipped over, but that's one way we can briefly explain. And so now back on the graph, this is the reason why on the original function x was 1 and y was 9, but now when it comes to the inverse function, on the graph of the inverse function, x is 9 and y is 1. They switch their values. Okay, and so now it's in that same way. Think about this next point right here, this other guiding point right here on my list for the red function, for the original function. 0, 1, 0 for x, 1 for y. Okay, so you can now already predict what should be or what will be the coordinates value for this point right here, for this point as the mirror refraction of that red point through the 45-degree line. Okay, so it should be, so now that reads 0, 1, so now I have 1, 0. All right, 0, 1, and now I have 1, 0. All we do, they simply switch place. They simply switch place. All right, and so now the next point, the next guiding point on our list, -1, -7. -1, -7. So now needless to say, that corresponding point on the transform graph, on the inverse graph, on the graph of the inverse, on the blue graph, has to be -7 for x and -1 for y. Okay, let's for all of us here being the beginners, let's take things simple that way. Okay, and so now I'm going to put a point here on my graph in blue. I'm going to put a blue point here at -1, -7, and we can confirm our result that that point should be a mirror reflection of this point right here. All right, so now -7, -1. All right, so that point at -7, -1, and here let's compare that with -1, -7. They are mirror reflection of each other. All right, and so now at this point it's becoming clear. The reason I mentioned this because now it will be time that we want to learn to also graph the function of a given inverse function. Okay, and we want to graph that together with the function in the beginning. And then once we graph it together, and the thing is we don't always have nice technology with us. So there are a lot of times we have to sketch by hand right there as well. Okay, or at least we know what to expect. And so in that way, knowing this property that the graph on the inverse is the mirror reflection, is the reflection of the graph in red right here through the 45-degree line will be a tremendous help. So now let's make that note down. Let's write down that note right there. Okay, so I would say I will write the graph of F inverse, okay, is formally speaking is the reflection. Okay, that's what we observed right there. It's the reflection, and that observation is really explaining well for a lot of students. Okay, so I just jump straight into this point right here without talking about any other fancy details. Okay, so the graph of F inverse of x is the reflection of f of x. Okay, through the 45-degree lines. And this 45-degree line really is just that line as an extra note, really line y equals x. Okay, and so the graph of the F inverse, and as extra clarification here, this graph is in blue, whereas the graph of f of x is in red. Okay, so the blue graph and the red graph, they are reflection of each other through the 45-degree line. Okay, that's all it takes right there. Okay, that's all it takes to sketch the graph, to draw the graph of any inverse function. Once we know the graph of the beginning function. So I made this demonstration right here, but now let's get into that example. And okay, so all right, so in that way, let me now take anyone learning in this video lesson to another example over here. And let's now call that example 3. So in this example 3, I'm gonna demonstrate, and we will learn the way how to just in general provide or sketch the graph of the inverse function from a given graph. So now let me finish writing down the worded instruction of this example. Okay, so let f of x be represented, so some function represented by the given graph. Okay. So in this example 3, I will be introducing a few problems. Each problem is a function that has a graph. And that's what it is right here. F of x is represented by the given graph. Okay? And we want to sketch So tentatively, this needs to be done by hand right there, so that you can catch that kind of skill right there. So sketch the graph, okay, of f inverse of x. So it seems like a very challenging work right there, but it won't be so bad. So we're going to have f of x given with the graph represented. And we don't have to know what function gives that graph, okay? But now once we have the graph, we want to take the picture of that graph and use our understanding about the relationship, the graphical relationship between f inverse and f to sketch the graph of f inverse. And so now allow me to bring in part A right here. So now part A is f of x with the following picture. All right, so this is my graph for part A right here. This is the graph for some function f of x, and this is for part A. All right, and so with that graph here, we want to sketch the f inverse. We want to graph the function of the f inverse. So here's what once again, allow me to really explain the step-by-step in this first problem right here in part A of the example. So we've learned earlier that, and now on the picture that we're seeing there, on the picture that I've shown earlier, so let's stay in that convention that the graph of the original function is in red color or in some chosen color. And then we're going to pick a different color to represent the inverse, the graph of the inverse. But now from what we have drawn out as a conclusion, then the graph of the inverse function is always the reflection of the original function in red through the 45-degree line right there, through the 45-degree line. Okay, and so I introduced that technique about constructing a table using the guiding points back in my lecture when I was going in real details about how to make transformation of a graph. We can use that technique again, the technique that focuses on the guiding points of any graph right here. Okay, so now with this graph right here in full screen view right here, allow me to show the guiding points. And guiding points, again, they are simply just those points on the graph that stays right on the grid. So I see one point right here. I see another point there. It's all just straight lines, straight segments between these points, these consecutive points like that. And so there's another point and there's another point. These are all the points that I can use them as the guiding points. They are useful in a sense that they define the shape of our graph. Okay, and so now I'm going to put the guiding points in. Okay, so these are all the guiding points. And then it's also beneficial to put in the graphical labels, I mean the numerical labels of these guiding points. All right, so this is our graph of the original function. We want to use this graph. We want to use that graph to sketch the graph of our f inverse right here. Okay, so the graph that we're seeing here is the graph for our function in part A. All right, so now when we are actually doing this, the best and the first thing to do is to put in the 45-degree line. All right, so with any kind of straight edge, we can easily draw a 45-degree line, assuming that our graphing paper assuming our graphing paper use a square grid right here. Okay, so now that's the 45-degree line. Or if we're using any kind of technology, then that 45-degree line is simply that 45-degree line right here is the y equals x line right here. And when you draw that, make sure you draw that just as dotted line, because it's not really a requirement, but it's just a good helping step. And another thing I have to mention, this problem, I really emphasize that term, we sketch the graph, because really we have no choice. Technology is not going to help us, in a sense that I did not provide, back to the picture of the graph right here, and as the problem is instructing, I did not provide the rule of the function, so we only see the graph. So some technology provided me that graph, and this kind of problem is still existing quite often in our practical the math textbooks, in our standard math textbooks out there. We have a graph given, and that is the graph of the original function f of x, and we want to go from that graph and sketch the graph of the inverse function, and we work completely without knowing the actual rule of f of x. That's the idea right there. And so that's why we only rely to our understanding that that the graph of f inverse is always the reflection, okay, of that original function through the 45-degree line. I emphasize this often enough now up to this point. So let's get to it. And so for that way right here, one more time, we're looking at the graph of f of x with these are what I call the guiding points. Okay, and so now with these guiding points now, I am going to record them as a table, and this is where that table technique that we used back in our time studying about the transformations, that same table technique apply here again. We can use it quite effectively. Okay, so for the original f of x, let's list down a complete list of our guiding points from the left to the right. And one more thing, this is needless to say, the problem is already asking us to sketch the graph of f inverse, meaning f inverse will exist. But we can also double check. Okay? We can also double check. This whatever function gives us this graph right here, this function here is a one-to-one function, because see, if we place a horizontal line, or if we rely right here to these horizontal grids, any of our horizontal grids only crosses the graph at one point. That's perfectly enough to show that this graph here in red came out as the graph of a function that is one-to-one. So this function here is one-to-one. And so being one-to-one, of course, it means the function will have an inverse. So don't worry about will we be able to draw the inverse or not. Yes, we should be able to draw that inverse because it will be out there, existing out there. Okay, but just what matters is we put our skills and our understanding into doing it, getting it done correctly. All right, so the first guiding point from the left to the right, according to the picture, I am seeing -7 and -4. And then another point, and I have to apologize to anyone viewing this lesson. I have to swing back and forth between the board here and my computer station. -3, -2. Okay. And then my fourth point to the right-hand side is 3, 7. All right. And then another point I have here is 7, 8. I have these points right here. These are the points on our original graph of the starting function. And so if we're thinking of the inverse here as a descendants function, then this original one here is the parent. Just think of that concept of a transformation. Because in the end, I still see the shape remains exactly the same. It's just we are now about to find our way to flip it as a reflection through that 45-degree line that you're seeing currently. All right, so in that way now, so let's get further. So we saw this earlier when I was doing that introduction problem earlier. So now for f inverse, this is everything we know, but that's everything we need right there. This is everything we know, and that's everything we need. On the reflection, on the 45-degree lines reflection of this function right here, then every point here will switch their roles, will switch their values. That's all there is. Okay, so now on the graph of the inverse right here, in other words, on the graph of the inverse, every point that was originally on the parent function will switch their role. So meaning the first point here, -7, -4, will become, so now I should use blue ink for this case right here. We will have the point being -4, -7. Ladies and gentlemen, it's that simple. The next point here, originally on the original parent function, f of x, it was that point -3, -2. We read that out from the graph. It stays right on the grid. So now the coordinates point becomes -2, -3. All right. And then the next point again, in order to show that reflection through the 45-degree lines, all we have to do is flip the values, the two values, like that. Switch the two values, swap the two values, x and y. So in my inverse function, it has to be 7, 3. And the last point here, now needless to say, 8, 7. We are done. We are done with that list of the guiding points. So these in blue now, they are the guiding points that we're going to use them to draw our graph on the F inverse right here. Okay, and so sketching this is going to be easy for this problem simply because, see, if we're looking at the graph more closely, it's just simply straight segments between any of these two adjacent points right there. Okay, so in that way, now let's go ahead and bring in all of our guiding points on the inverse function. So now, with my 45-degree line currently present here, let's look at the guiding points first. So these are now the guiding points. All right. So now relative to its original ancestor, each blue point here is exactly now in the way how we look like that. So there was no miscalculation or anything like that. See, I can show the labels like that. All right. So each point in blue color right here is exactly the mirror image of the red point originally. Okay, through that 45-degree line. All right, so now in that way, I'm ready to draw my actual inverse function. So as a hand sketch, then we just simply connect through these points as straight segments between each of these 2 points right there. Each of these two adjacent points or consecutive points. All right, so now, see, I'm going to draw my first segment, then my next segment. So everything we do in here, I'm trying to go as closely as possible to if we were doing that on paper and pencil. All right, and that's now the graph in blue here is the graph of the F inverse. All right, so just now we've constructed and this is the table technique, the table of values technique right here that we learned from our lessons about the transformation. But it's not the table of values, it's not the traditional table of values, it's just the table where I list down the guiding points that's making it easy for me to draw the shape of a transform graph. And the transformation happens here is the kind of transformation where we reflect through the 45-degree lines like that. And that's how it happens. Okay, all right, so you can see that same shape being retained. Okay, but it's going to be a flipped version through the 45-degree line. All right, so now I'm hiding that graph away for now. Let's put it in part B, and I'm going to show a different graph. And so same exact kind of problem in part B, and for each problem I'm about to provide in this example over here, you have a graph at start, so allow me to write down this is part B. Okay, so we have a graph. All right, so this is now the graph for our functions in part B. Okay, this is the graph of the original function f of x. Again, it's being in my convention throughout this lecture here, the original function, I'm going to use red color. You can have your own choice of color as well. But now we want to go from this function. And again, technology is not that useful in this case because we don't know and no one needs to know what rule gives this graph. Nobody needs to know that. But we already know, hey, it's a function. It has a graph given as such. We can double check that this function passes the horizontal line test, meaning it's a one-to-one function. And being a one-to-one function, it will have an inverse. And that's why we have this problem to handle. How do we draw the graph? How do we sketch the graph of the inverse function relative to this given one? All right, so now let's get to it. So now on the graph itself right here, I am going to first put in the 45-degree lines. All right, so the 45-degree lines is right here. So as the order of the work, as a certain order of work, see, once we have a graph given, we can always create a 45-degree line purposely for ourselves in the same graphing space. And of course, now with these problems, these kind of problems that I introduced in example 3 right here, needless to say, we want to draw the graph of the inverse function and the graph of the original function in the same graphing space, as you have already seen in example 1. I mean, in example part A earlier. All right, so now let's look more closely at the graph right here. And so in the complete full screen view right here. Now allow me to put in the guiding points of my graph. So the idea of the guiding points, again, they are nothing but just those points that falls right on the grid. So that's making it easier to recognize the shape. So I have a shape that looks kind of like a half cup here, a one-sided cup, and then it's a 45-degree line falling down from the left to the right, okay, and then it's another line here with some kind of slope right here. So it's easier, it's going to be much easier once we put in the guiding point. So I see a special one point right here, and any point here falls on the grid, and then there's a special guiding point here, one guiding point here, and one more guiding point here. That's define the shapes. So now let's put those in. Okay, so now we have those guiding points, and labels, numerical labels will be extremely useful. All right, so we got -4, 7, -2, 5, -1, 2, and so on and so on and so on. All right. So now I'm getting back to my board here, and let's write this down. Let's write down this is actually, when we are doing it on paper, we write it down in somewhere in our paper space right there, the table that lists down all the guiding points right there. So one column for the f of x. All right, one column for f of x. So the first point I see is a -4, 7. Okay. Then the next point I see is -2. Okay. And that's 5. And we have another one at -1, 2. All right, we have another one at 0, 1. All right, and then one more point we're having at 4, 0. All right, so these are the guiding points that I have on from my picture. Okay, and again, forgive me that I had to swing back and forth between the picture to read what's on my screen right there, to read the picture you're seeing right here. All right, so now with these guiding points, now here I'm ready for creating the setup guiding points on my inverse function. Okay, so now you have seen that throughout the last problem right there, we only need 2 columns. One column lists down the guiding points for the original function, and the next column here, the immediate second column, is for the final transform points as the inverse function. All right, so here we are. First point, originally -4, 7. Now it's switch. See, x and y switch role. Inverse function, x and y switch role. Inverse function, x and y switch role. So now 7, -4. That's it. Okay. -2, 5. Now for the inverse function, x and y switch role. So 5, -2. Okay. For the next point, third point down the list right here, -1, 2 right here. For the inverse function, x and y switch role. Okay. So now I produce 2, -1. All right. Fourth point on the list, down the list. Okay. Originally 0, 1 on the inverse function. X and y switch role. All right. 1, 0. Okay. And then for the last point here, well, we don't have to sketch all, because once we've made a successful list of all of these guiding points, the rest of them that we didn't list will also fall out accordingly once we retain that shape. Okay. And so now the 4, 0 on the transform on the inverse function, the x and y switch role. So now we're looking at 0, 4. All right. And so now let's put these successful guiding points, tentatively the guiding points of the inverse function, on the same graphing space here. All right. So now with my graphing paper, with my graphing space here in complete full screen view, now I'm putting in these points right here. Okay, I'm putting in these points. So it's starting to get a little, hard to keep track of right here. So once we put in these points, let's spend a minute trying to match the points. Okay, so I recognize this point is a mirror reflection of that. This point is a reflection of that. And so that means between these 2 points, these 2 adjacent points, it's a straight connection. And then the line extends infinitely out right there to the right. And so that means between these points right here, I'm expecting a straight line. And then that line is going straight out in that way. Okay, and so now here's what my graph looks like. And then between these 3 points, we have a parabolic shape right here, a parabolic shape. And these 3 points, now we already knew that this point is a mirror reflection of that blue right here. And so this point gets that mirror reflection right here in blue. Okay, and that other point is down here. So that means this here has to be that parabolic shape right there. Okay, and then this remaining piece right here is a line segment. So that explains that these 2 points have to be the line segment again. So now we are ready to sketch the graph. All right. All right, and that is now the graph in blue here is the graph of the inverse function of our original f of x in red right here. All right, and now we are ready for another problem. This one here appears to be slightly more challenging in a sense that it's not that it's a harder kind of problem, but it's just the shape itself may be a little harder to draw. Okay, so we just simply need to work on our the artistic skill a little bit in terms of drawing a bent curve that's satisfied. But in the end, we still stay with the guiding point, and that will tell the story. Okay, and so let me now bring up a function, the graph of the function in part C right here. Okay. This is the graph of the function in part C. All right. Nobody needs to know what the rule gives this function. It's a bent curve right here. It's a bent curve. Right? And then let's now attempt to sketch the graph of f inverse right here. So the graph here in red color, that is the graph of the original function. So now I'm going to come back to the computer station to bring that graph into the full screen view. And now in full screen view, we can go ahead and recognize the guiding points for this graph right here. Okay, so now for this graph right here, it has the following guiding points right here. And again, the guiding points, there's no fixed rules about how to choose the guiding points, but it's just easy to choose those points that falls right on the grid so that we can easily recognize the shape of our graph. So it's a bent shape, being a parabola or not, I'm not very sure. It looks close enough to a parabola, but basically it's a bent shape. And so now I see one guiding point right here falls right on the grid at 0, 1. I see another one at 1, 2. I see another one at 2, 4. I see another one at 3, 8. Okay. Whichever rule that is, that's not important at this point. And now let me show the guiding points. So these are the guiding points with the labels. All right. And so now, as our first or a prepping step before getting the transformation, before getting the graph of the inverse function put in together, then it's always best to put in that 45-degree line, because we want to see the graph of our inverse function as the mirror image of this line right here. Okay? And again, needless to say, this function itself already a one-to-one function. Okay? And you can quickly double check with that. Focus right on those horizontal grids right there. And any of those horizontal grids, it only crosses the graph at the 1 point. Okay? So now in that way, I'm ready to tackle down the graph of the inverse function. So now I'm going to sketch that table again. I'm going to draw that table that contains all the guiding points. So f of x, okay. The first point I saw there is a point 0, 1. And again, I have to keep apologizing, viewers, for keep switching back and forth between where I stand here and the computer station. And then I have 1, 2. I then have another point at 2, 4. Okay. Whichever rule that gives this function, if you recognize that, you can hold it for yourself. It will be beneficial for the later lectures. But right now, that's not what we need to know. We just simply say, hey, we have these guiding points, and through these guiding points, we have that kind of shape right there, kind of like a bent shape pointing up from the left to the right. That's all we need to see. The next point here is a 3, 8. Okay, so now I have those 4 guiding points. Now I'm going to make my attempt to draw the guiding points on the inverse function. So inverse function, all right, we'll have the following guiding points. First point at originally 0, 1, now switch to, is now transformed to 1, 0. Again, on the inverse function, x and y values switch role. For that next point, originally 1, 2, now on the inverse function, x and y values switch role. So now that's why we're having 2, 1. Okay, on the third point down the list right here, originally 2, 4. Now on the inverse function, again, x and y values switch role. So 4, 2. And then the last point here, needless to say, 8, 3, because x and y values switch roles. All right, so now these in blue color, and that's the only column aside from this original column that we need. So now we're going to put these guiding points in blue on our graphing space and really pretend that you really are doing this, watching and doing your graph at the same time. So I'm trying to make my technology run like as if we were doing a hand sketch version. Okay. And so now with my graph in complete full screen view right here, let's put in the guiding points. All right, so now we can double check that any of these points is exactly a mirror image of that of its parents through the 45-degree line right here. And having numerical label, showing the numerical labels would be a good idea for these points. And now we are ready to sketch. So when it comes to sketching anything that's curved, I'm not the best. And I don't blame anyone for not being able to get the exact bent curve. We're not trying to race with machine. We're not trying to compete with machines. We're just doing the best we can. Yes, Desmos here gives the best looking picture. You don't have to. Okay, but get the shape that shows enough, the shape similar to where the parent function came from and being the reflection of through the 45-degree line. That's already fair. Okay, so now I'm going to draw the curve. All right, and that's how the curve looks. So now the two functions, with these two functions, they are mirror image of each other through that 45-degree line there. And so this graph in blue right here, yes, it is the graph for our function, whatever function that is, that's in red. Okay, and we will learn that some time later at some lecture outside of this lecture, you will learn what rules give these guiding points there. All right. All right, and now I have an FYT for anyone viewing from this lesson, learning from this lesson. So just like that, just like how I have been doing with the 3 problems there with a lot of details, then now for an FYT, I won't have to show my details anymore. You can just spend your own time to get the problem done. Okay, so I will show the graph for this particular FYT along with the guiding points on the original graph of the f of x. I want you to spend your own time constructing your own table, do whatever that I've taught so far throughout the entire example. Get your graph of the inverse function sketched together in the same graphing space. And feel free to pause the video. Once you can resume the video, I'm only going to show the final graph like that. All right, so here we go. This is the graph. All right, so this is the graph for our whatever function that is, but it has this graph for our, as you know, the graph for f of x. Okay, we don't have to know what rule gives this function, but now from this function, let's draw the graph. Let's sketch the graph of the inverse function. All right, so now assuming that you are resuming with this video and already spent some time working through your steps, then this is the graph of our inverse function in blue. Okay, The guiding points are here with labels. All right, and to make it really clear, this 45-degree line right there tells the exact story how each point here is a mirror reflection through its parents. Okay. All right, so let's now look at a very important property that anyone learning about inverse function must know. Okay, so this property is named differently throughout many textbooks. Allow me to use this name that I really like from one of the textbooks that I read. So this is called the Roundtrip Property. So like I said, other textbooks name it differently, but this particular textbook here, I found this name quite interesting. So I use with that name here. So let's look at this, what's so-called a roundtrip. Okay, the roundtrip property. But in the end, once we understand about this property right here, then it's a very important property on its own for anyone learning about inverse function, as I said earlier. So here's how the property is stated in words. So allow me to write the stated, the worded statements first. So if f of x has an inverse and yes, in our notation here, the inverse function of f is now that symbol. So if f of x, some function, any function, as long as we know if it has an inverse. So if f of x has an inverse, okay, then it must be true for the following. Taking the inverse operation on f of x. Okay, so f inverse of f, that must equal x. Okay, and the same thing, the same way with f of f inverse of x. This must also equal x. Okay, so I have to clarify it again. This is the important part right here, but now make a note right here. I write this note in red ink, so the major part to understand is here. But so this x right here is the x that belongs to the domain of f. So, and that's why right now I just want you to focus on this property, and then talking about the domain, we will get to that later, but just as clarification. So here, I can add in a line right here that says, for every x in the domain of f, okay? And then this here is for every x in the domain of f inverse. So I wrote this extra one right here, not really to emphasize it so much yet at this point. We will get to that emphasis later, but right now I just added in because it's for extra clarification, but the main thing you need to focus is this property right here, f inverse of f equals x, okay? And then on the other hand, f of f inverse equals x as well, okay? So now, why is this so important? And first of all, let's look at how we can use this. Let's look at what we can do with this, okay? And so now, let me show the following demonstration problem right here. All right, so back to the earlier introduction. When I brought up f of x equals 2x plus 3. I pointed it out and I made a lot of explanations, and we came to, so at this point we were clear that f inverse here that's x minus 3 over 2. These two are completely different functions. They're separate from each other. They are related. They are connected. Somehow there's a connection that relates them, but in the end, these are two separate functions. Okay, but now one thing I know for sure. So now with this property that we just now learned, this property, this round trip property says f inverse of f. Now, there is a reason why, there was a good reason why I said in the beginning of this lecture that it is highly recommended that we learn this lesson after you have learned about composition of functions, because this is what it is. Right now I'm about to, as a demo, I am about to take f of x, and I'm going to compose a f inverse with f, okay? Or this is f inverse of f right here. All right, so now back on this right board of mine right here. F is here, f inverse is here. Okay, so just for you to understand how this property works. So now this is what I'm going to do right here. I am going to create that composition of the two functions. I'm going to put f inverse outside, and now I'm going to put f of x inside. So for anyone who has already learned about composition of functions, you should be familiar with this way of setting up. We're putting one function inside another function. So in other words, right now in the way how it looks, according to the order, then f inverse here is the outer function, and then f of x is going inside as the input of f inverse. Okay? And so in that way it means my function f inverse right here, right now I'm still writing that the same way, but this function f inverse is going to take the expression 2x plus 3 as its input. The way how any function is that the function takes an input and apply its rule. So f inverse is a rule on its own. This is the rule saying that input minus 3 and then divided by 2. But now we have already learned this, and we even had some lecture on the advanced kind of problem where we substitute an expression as an input for a function. This is what it is. And then altogether the idea here is that f inverse is composed with f. So I'm taking f of x. So f of x is represented by this rule over here. F of x is this rule, 2x plus 3. And that's why I took 2x plus 3 as the input for f inverse right here. All right, and so now we are ready to proceed. And so again, as you recognize, as you now realize that this kind of work, particularly here, is heavily based on our understanding about the composition of functions, then in case you're still feeling in any way a little shaky with your skill on composition of functions, then you can feel free to pause this video, review my lecture about composition of functions, and then you can go ahead and resume. Okay, but now once you resume, that means I can assume that in this video I can keep, once you resume this video, I can assume that you have already been fluent with that skill about putting an expression inside another function. Okay, so now let's continue. And so here in this way, f inverse is this rule where it says for every input we're going to take away 3 and divide it by 2. For every input we're going to take away 3 and divide it by 2. Okay, and so but now the input is this part that I underlined with the brackets right there, and that means the inputs, for every input the inputs currently substituted in is a 2x plus 3. So for every input I'm going to subtract 3 from every input. And again, in my style, I heavily used, and it should be a good practice for anyone doing math, use parentheses. Okay, so 2x plus 3 as the input. Subtract 3 and divide it by 2. That's the setup for now. The setup right after setting up f inverse of 2x plus 3. Okay, and so in that way, now the algebra, the elementary algebra steps are coming out. We're going to take away parentheses and then combine like terms and start simplifying our expression here. Okay, because right now the expression looks a little complicated. Okay, so we're going to simplify it down. We're going to make it look simpler. Okay, so since the sign in front of this, the sign in front of this pair of parentheses here is a positive sign. Okay, so we can just safely take away the parentheses without changing the sign here. And so now in my next step, I'm going to rewrite this expression now, but without parentheses and no sign changes. So 2x plus 3 minus 3, and we still have a division. We still have that denominator here. Okay, so now we took away parentheses. Now we recognize like terms. Okay, so the algebra steps is telling us that we can cancel the like terms, and as a matter of fact, these are opposite terms. So we're going to produce, that's the work there is going to yield for us 2x over 2. And now with the elementary algebraic understanding, we know that we can cancel this common factor 2 from numerator and denominator of this fraction. So 2 got canceled away. So now my final step ends up with x. That quick demonstration here clarifies what it's stated here. Clarify what it's stated here, that this function, I mean, anytime that we know f inverse, anytime we say that f inverse is the inverse of f of x, anytime we say a function is an f inverse, is the inverse of a function, then taking that composition will land us into this simple x value. Okay, but now I need to do one more demo, because the demo I've done so far is only half of the story. Okay, it must be also true for the other way around. So the opposite way of the composition is here. Now I'm going to put f inverse inside of f, and I want to also make sure that it lands into an x. So let's demonstrate the idea right there. Okay, and so like I said, this demo right here was only to bring that round trip property to light, for you to have a practical look at that, for you to have a real clear understanding of what it says right there, of what it's said. All right, so just now I put the actual f inside of what we so call the inverse. Well, we have learned already through the earlier lecture that this was the inverse. We made that conclusion. So now once we arrive at that inverse, then for sure this property will happen. F inverse of f equals x. It was just demonstrated here. Okay, so I use this demonstration as an informal proof of that round trip property. As a matter of fact, it was formally speaking, it is, and it was a theorem that came out from that was proven in math. But now in standard pre-calculus textbooks, we call that it's a property. Okay, and so let's look at the other way around. So now, once again, we already knew from earlier discussion that these two functions have inverse relationship. And then I'm saying that relative to f here, then this function here is f inverse. Okay, and then this function here is also the inverse of the inverse its own. Okay. So now I'm going to do f inverse of x. I'm going to purposely set up this composition of the two functions. But this time I'm putting the f inverse inside of f. It's the opposite way. Okay, so from the inside out, f inverse is inside as the input. So f inverse, now the f, see this symbol right here, I say that f inverse as relative to this one here being the main function. So I put the f inverse inside of the function f. Let's see what's going to happen. Okay. So f inverse is this rule right here, where it says for every input of f inverse, we're going to take away 3 and divide it by 2. But at this point, I'm seeing that as an expression. I am going to take that expression and substitute that into our function f. So now that means, and again, once you have learned about composition of function, this idea that we're putting an expression inside a function as an input of a function, that idea is not new any longer for any of us viewing this lesson. Okay, and so now this is the same as f of x minus 3 over 2. One expression, but being used as the input for our function f. Okay, And so now in a familiar term, we are going to plug this expression into our x variable here of the function f. So the rule of f says for every input, we're going to multiply by 2 and plus 3. That's the rule of f. But now f is going to take this input, this big, crazy looking input. And so in that way, but the rule is the rule. The rule says from whatever the input is. Now currently being x minus 3 over 2, I'm going to multiply that input by 2. Okay, and I'm going to subtract 3. That's what I will be doing. And so now the math is going to start coming out, because here we ended up for ourselves an expression. And now we're going to start simplifying this expression. All right, so now I can see that in my next step, this 2 will cancel. So according to the order of operations, we must cancel this common factor instead of subtracting those. All right. And as a matter of fact, I just now realized it should have been an add. Okay, and so now canceling the common factor 2 right here gives me x minus 3 and plus 3. And now minus 3 and plus 3, these are opposite terms. We can cancel them, and we ended up with x. So that little demonstration here, once again, just now proven the statements stated in this round trip property. As long as we know this function f of x has some inverse, and we call the inverse this f with the symbol, superscript -1. As long as we know they have the inverse relationship, then this statement here is also true. We just now demonstrated that idea right there. We just now demonstrated that idea in the other board with that little problem. Okay, so now let's see how this property can be useful for us, because so far I was just proving it and brought it to light right there. Okay, but now let's look into an example to see how useful this can be. Okay, all right, so and now allow me to present example number 4. All right, so the worded instruction here is quite simple. Are the two given functions inverses, okay, of each other? Are the two functions inverses of each other? Okay, let's have a look. So the idea now is that we're going to be given two functions. One of them is, and we don't need to, and that's the point, which is now simply given out two functions. We want to find out, according to this way of worded, how the problem is worded, we want to find out whether the two functions given here are inverses of each other or not. And so in that way, do expect that they are not necessarily f and then f with the superscript -1. They can just be named anything. So here I call it f, one of them, one of the function. How about 4x plus 2? But then I have another function g of x. See, and it should be the way it is. In this problem, it should be avoided to use a f inverse here, because we don't know if they are inverses or not, and that's what we want to find out. Okay, and once we found out and clarify and verify, then yes, g can be the inverse, but that's all up to what we need to investigate right now. Okay, so now that's why these are in the end just any two separate functions. I have to give them different names because we're working with both of them at the same time here. So now g of x. All right, so how about g of x here is an x minus 2 over 4. Just any two functions. Now we want to discover whether they have that inverse relationship between them. Okay? And so now this is what I do. So first, I am going to put f inside of G. And that's just exactly what I said. I'm going to put f inside of G. So in this setting right here, yes, from our understanding about composition of function, this is G of f. So you can think of this, yes, as G circle f of x. That's one way of writing it. But I see that this is easier to understand a little bit. Okay, I'm putting f inside of G. So that means now as far as the idea of composing functions together, or composing G with f right here, then I'm going to put this expression that represents f inside of G. So now that means in the next step, I'm producing G of 4x plus 2. Because right now, in the way it reads, G of f, G of f, G of f. So f is the input, but f is this rule itself right here, the 4x plus 2. And now we see that as an expression being in place of an input of the function G. Okay, and so now, let's advance. Now things work just like, things appear to be just like that demonstration I did earlier. I'm going to just proceed into the math right here. Okay, so in my next step, G of 4x plus 2, the rule of G says for any input we are going to take. On any input, I am going to take. I'm going to subtract 2 from the input and divide it by 4. Okay, so in that way, this is the input right now. The input is currently this entire 4x plus 2 expression. So 4x plus 2, I'm going to take away 2 over 4 because it's G of f. It's G of f. So f is currently, with f currently being the input, I plugged that into my variable of the function G right here. Okay, I plugged that into x of the function G. Okay, but precisely speaking, once I see this entire 4x plus 2 as an input, then from the rule, from what the rule stated here for G, input minus 2 all over 4. Inputs, big inputs, minus 2 over 4. And now we're going to continue, we're going to proceed with the math to simplify down our expression. Okay, and so here I'm looking at, I can take away the parentheses without changing signs, without flipping the signs of these, because in front of my parentheses here it was a positive sign. Okay, and I'm going to subtract 2, and I'm dividing by 4. All right, so now some opposite terms are being displayed here. I can cancel those two opposite terms. That leads me to 4x over 4. And now with this current fraction here, with this current rational expression here, okay, I am going to cancel that common factor 4 away. Okay, and now I do land into x. All right, so I have just now verified that G of f equals x. Okay, so conclusion here, G of f allowed me to use the friendly function composition symbol. G of f of x equals x. So that's satisfied. One statement right here, because this is right. Because you see, this statement, the round trip property was written in terms of assuming that we already knew this. Okay, and then at the end of this example, I'm going to add in another statement right here, and then for now, allow me to take away this extra details right here, and I will get back to that later. Because right now we just want to focus on the practical usefulness of that. Okay, and so let's check for the other condition right here. We want to see if these two. Now, if I put f inverse, tentatively I want to see if G is the inverse of f. So I have to go the other way as well. I want to put G inside f. Okay. All right. So now I need to erase this space right here. All right, so now I am going to put G inside of F. So I'm going to do F of G. Okay, so just earlier, I verified G of F. It was equal to X. We got that verified. And now I'm going to do F of G. That now here gives me, so now G is playing in place of the input of F. Okay, but G is this rule over here. X minus 2 over 4, or that expression X minus 2 over 4. So I'm going to take that expression and substitute that into our function F as the input. So now F now takes the input as the entire expression, X minus 2 over 4. So F is now going to take X minus 2 over 4 as its input. Okay, so that means we are going to do, the rule for F says, for every input, the function F is going to apply the following rule. For every input, it's going to multiply by 4 and plus 2 to the input. Multiply by 4 and plus 2 to the input. Okay, and so now I'm looking at 4 times the input, because from whatever the input is, I'm going to multiply by 4, okay, and then plus 2. And that's how the setup came out for me. And so now I am going to cancel that 4. Now I'm on my way to simplify the expression. And then it leads me to X minus 2 plus 2. And then I realize I can now cancel out the two opposite terms here. It leads me into another X. So now I make another conclusion. Okay. F of G of X also equals X. So this is another discover that we just discovered regarding these two functions. They have that special relationship. Okay. So let's put the pieces together here. So these are just all the work here, but now let me sort of summarize our thoughts together here and put in a general conclusion. So as far as the two given functions here, we have recognized, we have proven the following. We have discovered, that's more like the better word of saying, for these two given functions here, we have realized or we have discovered the following relationship. First of all, if we put G inside of F, we had that result turn out X. We just now had that done. I showed the work and I just had to erase that. Put a check mark there. Okay. We also did G of F. We put F inside of G. That was the work even before this. And I erased that already. We also got X. So we have these two requirements. We have these two satisfied. And so now here's the thing. Now we use this. Okay, we use this to lead to a final conclusion, because the main concern here about these two functions given here is that, are these two functions inverses of each other? Okay, are these two functions inverses of each other? So now I'm saying yes, satisfying these two requirements. I'm saying yes. Okay, F and G are inverses of each other. Such a powerful statement. It means F is the inverse of G, and also G is the inverse of F. So let's make a note here. If we look at G as the main function, then F is the inverse of G. That's how I notate that. F is G inverse. And at the same time, we just proven G is F inverse. That's what it is. Okay. So I have to point out this final detail before we move on to the next part of the example here. Okay. You can pause the video and look at the work structure a little more closely. Okay, and start putting some logical thinking in here. Then, as a matter of fact, with this work right here, I'm cheating around a little bit. Okay, because here's the thing. Now, if we look back at this statement in the way how I wrote, logically speaking, we will know these two if we knew the two functions have an inverse relationship. Pause the video or rewind the video to think of what I said, or to hear what I said again. Okay? In the way how it's worded here, we will know these two if we already knew these two functions are having inverse relationship. Isn't that a little bit opposite, logically opposite with the work we're doing here? Because the work we're doing here, we're not in that position where we have already known these two functions are inverse. We are not in that position. Okay? But it looks like the way how the logic here is being used. It looks like the logic being used here is that we want to use this as a way to make that conclusion that, hey, these two are inverses. We want to go from knowing this, because we can do the math to know this, and then we want to use that to make a conclusion about these two functions are inverses of each other. I mean, we already made that conclusion here, but I just want to point out to light that the logic of this problem so far is the opposite logic of our round-trip property. Because this, in the way how it's stated here, it's only said that if we knew these two being inverses, then we will have these. But now in the work that we've done, we knew that we had this. Okay? And then we try to use that as a way to make conclusion that these two will be inverse of each other. So now that means I'm going to go back here and make the final completion of this round-trip property, because so far what I wrote down here was only a little bit more than halfway. Okay, so now I call these the two important properties, right? Now allow me to word it this way. It is okay at this beginning level over here to understand this way of wording it, even though it's not the formal way of stating it. And the converse is also true. And the converse is also true. Okay, so what do I mean by the converse is also true? It basically means, just think about the example I just now finished. That little problem I just now finished. Once we can prove that any two given functions satisfy this relationship, then we can say that they are inverse of each other. They are inverses of each other. That's what it means by the converse is also true. That means if we think on the opposite way, if we think the opposite way of the logic. So right now, in the way how it ends up to here, then we must know if these two functions are inverses. Then we will know these two little properties. But now the converse is also true means for any two functions, like in that example I just finished. Like that example I just finished, for any two functions, if we know these two properties satisfy at once, then we can lead to that conclusion that the two functions will be inverses of each other. That's why in one short statement, I apologize that, at this level over here, I just try to reduce the amount of wording. And so this is not the formal way of saying it mathematically. It really bothers me a lot. Okay, but on the practical side, for a beginner to learn this, just using short words, hopefully it will make it better. Okay, so just think about we can work with this in the opposite logic as well. So as long as you can bring to light that any two functions satisfy this requirement, then we can make that conclusion that the two functions will be inverse of each other. Any one of them will be the inverse of the other one. Okay, and that is how useful this now become actually a theorem. That is how useful we apply that round trip property into this problem. We started out with two given functions. And then from these two given functions, we purposely did the math work because we were brought into that direction. We were brought to that question that hey, these two given functions right here, are they inverses of each other? And so we did our math work and we came to this conclusion first. And then from this conclusion that we recognize from these two conclusions together, from these two observations that we made together, now we made that generalization, we made that conclusion that, hey, then in the end, f and g are inverses of each other. Okay, so it's really, this is really the opposite of that logic, but in the end, the round trip property now is, and really it's a logic that's going two way as well. It's a round trip logic as well. So you have two functions that you know being inverses of each other, then they have that they will satisfy these two requirements. Okay, and then as long as you know any two functions that satisfy these two properties, they will have an inverse relationship. Okay, so the logic is going round trip, but really the name round trip here is not because the logic goes round trip. In math, there will be a lot of properties that going round trip like that. But the real round trip, the real thing that makes it round trip property is simply because, see, if you're going inverse of f, inverse of the f itself equals x, and the other way around, f of inverse f is also equals x. Okay, so we're going one way and the other way back. That's why it's called round trip. All right, and so now let's continue with example 4 right there. So now I am given another set of functions, another two functions right here. All right, so how about f of x equals cube root of x plus 1. All right, and then our g of x is given as x plus 1 all cubed. And as a matter of fact, I need to correct this. This is a minus sign like that. Okay, so we want to find out, we want to check if these two functions are inverses of each other. Okay, and so once again, we want to then, in order to make that conclusion, yes, they are inverses of each other, or no, they're not inverses of each other, we have to do the following. So first, I am going to put g inside of f. So this is how it works. I'm starting out with putting g inside of f. So now g is this expression. G is the representation of that entire expression. I am going to substitute that expression into my function f, into the input of my function f. All right, so that means now from what it says here, this is f of x plus 1 cubed. I take the entire expression that g represents and put that inside my function f as an input. Okay, and so now in the way how it appears, and at this point we have seen this often enough. The rule of f says for every input, I'm writing down the inputs for f right now. The rule of f says for every input, we're going to subtract 1, and we're going to take the cube root over all. Okay, we're going to take the cube root over all. All right, and so now allow me to do the following. We now need to simplify this. Cube root of the perfect cube inside of the root here, you got to be careful a little bit. It's not going to nicely cancel with that cube root. This cube is not going to cancel with that cube root because indeed it's a cube root, it's a perfect cube, but subtract 1. So we have to see if we can FOIL this out and simplify with 1 like that. Okay, so let me make a small note in red ink right here. So think of this here as x plus 1 times x plus 1 times x plus 1. If you have faster trick, go with that. Okay, but in the worst case, if you have not picked up any faster trick, that's what I'm showing right here. Think of this cube as x plus 1 times x plus 1 times x plus 1 and start foiling. So in case that you need to pause the video, go for that. Okay, but now allow me to assume that you have already done some work and verified me. Then the final foil work of this will land into the following. Okay, and of course, I mean, writing a lecture like this, preparing a lecture like this, I have to get certain things done beforehand as well. Okay, so now with this, after the foiling work right here, I'm ending up with, and I'm talking about before subtracting 1 right here. Only this foiling work will give me in simplified final form. I'm looking at x cubed plus 3x squared plus 3x plus 1. Okay, and now it comes a minus 1 inside the cube root. All right, so we see some lights. We see some lights that we can cancel the 1 here. But then after canceling that 1, we are about to run to the dead end just right there. The dead end is just right about here. We just can't get our way. We just can't get our way to make it equals x. We just can't. It's just not going to equal x. Okay, it's just not going to equal x. All right, so immediately what does that tell us right here? We fail that requirement, and as long as we fail one of the two requirements. Now think about the logic. If it passed, then we have to check for both, but now it already failed one of the two requirements. Okay, and so in that way, I don't need to proceed any further. Now I can just say f of g of x as a conclusion is not equal to x. Okay, so in that way, nope. F and g are not, okay, inverses. They are not inverses of each other. Right, and so that's another problem of how we operate with that. But once again, in the end, we're trying to use that. We're trying to discover whether they have those special two properties, and then once we know both of those, and we're trying to make our way into that conclusion, these two are inverses. But in this case, one of the property already failed. Okay, we even brought to light that it fails meeting that requirement. So we also treat these two. Okay, it's a property, but it also now becomes a requirement for any two functions in order for them to become inverses of each other. Okay, and so let's look at another problem. All right, so now in part C of our example. Right, so let's look at another pair of functions. How about f of x equals all right, so how about 5 over x plus 6 minus 2, and then g of x equals 5 over x plus 2, okay, minus 6. We want to find out if these two functions are inverses of each other. Okay, we want to find out if these two functions are inverses of each other. So once again, we need, in order to say at this point I've done two problems, one of them passed in part A, and I had to step back over to the property to explain some more about that, and then we went on to part B. It was a no, and now in this part C right here, let's recap things again. Basically, we just need two properties satisfied. One of them, we just need to make clear that f of g equals that. We just need to make sure that, and also g of f to also equals x. If any one of these fails, then these two will not be inverses. Okay, so let's start our work right here to first verify this, and verify the next one. So if one of them works already, we have to move on to the next one. I mean, if whichever the first one that we start, we can start with that one first and then that one later. Whichever the first one works, we have to move on to the next one. So if one of them works, we have to make sure it works on both. Okay, so now let's test for f of g. Okay, so f of g says, so now f of, so g is this entire expression right here. So 5 over x plus 2 minus 6. The entire 5 over x plus 2 in the denominator, and then minus 6. That entire thing there, okay, will be placed, will be in place of the inputs for our function f. All right, and so now we are ready to advance. So now I highly recommend to make common denominator and bring these two terms. Before I even plug that into my actual rule of the function, I recommend putting this as a 1 fraction. And so one more step, I'm still writing it out in the form of f of the input. So now 5 over x plus 2 minus 6, making common denominator, we're looking at x plus 2 as the common denominator. But now I'm looking at minus 6x minus 7. Okay, minus 6x minus 7. That's, so you can always pause the video and double check with my work right here. All right. The reason I did not go over that work in detail because it was meant to be, you know, part of your learning from the prerequisite course right there. All right. So, and you can always get a hold of me outside of the video lecture here for extra clarification. Okay, so now I'm having a large expression here. I'm putting that entire large expression here in place of the x variable. Okay, so now I'm looking at 5 over, okay, and then now I'm looking at minus 6x plus 7. I mean, minus 7 all over x plus 2. Okay, with all of that expression plus 6. All right, and then minus 2. Yes, I do admit the problem becomes large a little bit, okay, but it won't be so bad actually. So in my next step, so I will bring these two, so this is 1 fraction plus a number, and those two terms together stays in the denominator of a bigger fraction. Okay, so let's now leave that 5 on top for now. Okay, let's make common denominator to bring these two terms into 1 fraction. All right, and so once again, the work for finding common denominator, we're looking at minus 6x minus 7, okay, but then plus, and then 6 times x plus 2. That's just, and hopefully that revealed a little bit of your skill about finding common denominator. And this was a common denominator x plus 2. So this was 1 fraction in the big denominator, okay, and then minus 2. All right, and so now I will advance to my next board for the continuation of this work right here. All right, so in my next step, carrying over from the previous work right there, now it's 5 over, okay, and then so now it's going to be 6 minus 6x minus 7. There's no need. I can now take the parentheses away plus. Okay, so from my previous step, I can, in this little numerator, I can distribute that 6 for each term of the x plus 2 like that. So now I'm looking at 6x plus 12, and all of that here is over a denominator of x plus 2, and then here's minus 2. All right, and so now I am getting into my next step, being, so it's still that 5 here. This numerator here, we can start combining like terms, and a lot of opposite terms start coming out already. Minus 6x and plus 6x. Those two cancel. Minus 7 plus 12 is a positive 5. So now I'm looking at, and so I just realized now that I made my fraction a little too gigantic, because after all it reduces down to 5 over x plus 2. And then don't forget we have that other minus 2 right here. All right. And so I hope that I'm briefly reviewing some of your skills from the previous course, but any of these terms about simplifying a fraction where the denominator has another large fraction, you should have learned all of those skills from your previous course. Okay, your previous course, your prerequisite course built those skills, and we use those skills and apply that in here for different kinds of concepts. Okay, so now 5 divided by a fraction. So in my next step, I'm looking at 5 times that fraction x plus 2, but over 5. A fraction, I mean a value divided by a fraction, we multiply that value by the reciprocal. Again, it's a skill from previous course, an understanding from the previous course. You should have learned that already by now. And then minus 2. Okay, and so now I'm going to cancel that 5. All right, and so now in my next step, I'm reducing that. And so now starting that scary point, then in every next step, things keep breaking down significantly and significantly. And we keep getting things reduced down and reduced down. So now I'm going to reduce my expression down to x plus 2 minus 2. And now cancel the 2 away. We're ending up with x. All right. It's a very nice ending point right here for us. In what way? Now we have made that conclusion about the two functions that we've had. F and g given here. F and g given here. I have found f of g does equal x. We found one of them. All right, we found one of them. But that's just one. We need to now also ensure g of f of x will also equal x. That's why I'm putting question mark right now. We want that to happen, but we don't know if it will happen or not. Let's find out. All right. So now back on my other board again. We're going to throw in the later half of the work. All right, so now I'm going to start out with g of f of x. I'm putting now f inside of g. That means here I'm looking at g of f is this rule, 5 over x plus 6 is all minus 2. So 5 over x plus 6 minus 2. And just like the previous step I was doing, it's better if we bring these two terms into one fraction. So it's going to look as following. G of, and then your skill of taking common denominator and combining the two terms into one fraction need to be brought back in here. So allow me to skip that deep explanation here. And I'm only going to show the final one fraction after combining the two terms here together. So here I'm looking at minus 2x minus 7 over x plus 6. All right. And so now I'm ready for advancing to my next step. Just notice that this gigantic expression is now acting in place, is now playing in place of our inputs of the function g. This is g. This is g. Okay, we're going to take this entire input, substitute that in g. All right, so now this is for g. So that means in the next step, I'm having the following. 5 over the inputs plus 2 minus 6. And that empty parentheses here is being ready for this gigantic input. That's why I put it so big. Minus 2x minus 7 over x plus 6. All right, and so now we definitely have to simplify this and keep simplifying it until we reach 2 equals x, tentatively. Okay, And so now, again, apply your own skill to bring these two terms in that big denominator into one fraction. So for now, let me circle that in red ink. I didn't do this in the earlier step, but now I just realized in my mind right there, maybe I should circle that particular part. You can think of that as one separate little problem where you combine a fraction with a term and combine them into one fraction and put that all in the denominator of this overall larger problem. Okay? So in that way, this is how I'm seeing it. Now making common denominator, then I can multiply this x plus 6 with that 2 right there. So now it gives me 2x minus 7, okay, plus 2 times x plus 6, okay, and all over x plus 6. And then there's a 5 still here, and then there's minus 6 is still here. All right. And so now in my next step, I can just go ahead and distribute that 2 for each term here, because right now it's in product form, 2 times in quantity x plus 6. So I'm going to distribute 2 for each term there. All right. So in that way, in my next step, 5 over, so there's a minus 2x minus 7 plus 2x plus 12 all over x plus 6, and then now minus 6. All right. So in my next step, I can already see that the minus 2x and the plus 2x canceled. 12 minus 7 will end up with a, so that's 5 over x plus 6. That's how it's reduced to. And don't forget, after this fraction, we need to subtract 6. All right, so things start reducing significantly in every step we move now. And then now in the next step right here, you see I can now, similar to the earlier work, it's 5 times, and now this fraction in the denominator need to take as the reciprocal. So I'm going to multiply this 5 with the reciprocal of this. Okay, so it's x plus 6 over 5, and then minus the other 6 from there. Okay, and so now this 5 will cancel with that 5, and now it gives me x plus 6 minus 6. Now I'm going to cancel that 6. Now it leaves me x. All right. So what else have we found? Just now we have done, from the starting point we were firing up g of f. We work our way through, and we ended up with x. So now let's make a conclusion. So g of f is also equals to x. So this means we have found, so and earlier we found f of g already equals x, and now just now we found g of f also equals x. So now we are ready for making our final conclusion. Yes, f and g are inverses of each other. That's how it works right there. All right. And so now before I leave this example, let me provide a quick FYT problem for anyone viewing this lesson to give it a try. So on this one right here, you can spend your own time working on a problem without my explanations here, and I will only point out the final answer. Okay, so as an FYT, here are the two given functions in this FYT inverses of each other or not. So here we go. F of x equals cube root of x and g of x equals x cubed. Okay, all these two functions inverses of each other. So go ahead and spend your time finding out, do that check right there, do that checking work, and then find out if they are inverses of each other. Okay. All right, so hopefully you have had some pause time with the lecture and had your own work done. Now as you resume this video, the answer is yes, they are inverses of each other. Okay, and then the work that was for you to give it a try. All right. All right, so now after we finished with this example 4 over here, and particularly we apply that rule that we've learned about the round-trip property right there. So let me now briefly discuss about what's the impact of this kind of problem in example 4, this kind of problems in example 4 over here. What's the impact of that? I mean, it was not just brought up because we have to do it. Okay, it's not that. It has a good application, it has a good usefulness out there. Okay, so let me bring up the following scenario where you will immediately understand the good purpose of this kind of problem. Hey, you have two functions and we have to check whether they are inverses of each other. Okay, and allow me to make it brief and in a sped up page right here. So I recall from one of our earlier example, particularly example 2, where I was showing how to find the inverse. Let's pick up on this function. Let's say we started out with f of x equals 2x plus 7. Okay, and then we worked our way up. And we found we worked our way up. And allow me to actually show the process a little bit. So the process said, first we wrote that as y equals 2x plus 7. Okay, nothing unusual. And I purposely want to point out that a lot of times we make errors all over, even though we already had the valid technique right here, the solid technique. We replace the symbol here with a y variable, and then we interchange, yes. So x becomes y and y becomes x, so 2y plus 7. And then now as part of our process in solving this, we may become a little overconfident in our own algebra skill. It happens to a lot of math students, and including me. Okay, we make errors. So our mind tells us to take a subtraction, yes. But then who knows, at some magical points, at some magic point, we wrote this as an x plus 7 equals a 2y. And then from that point on, we led to further error, provided no matter how correct we were taking with the later steps. So we ended up with y equals x plus 7 over 2. And without anyone ringing a sign that, hey, you got an error somewhere in your steps here, we're going to start telling our mind to accept that this is our final f inverse, or the inverse of this function. It happens. I was a student once, and errors like this I made all over. Okay, and so now in that scenario, you don't want to, and we got quite a few steps here, especially for the kinds of problem, for the anytime we're working with functions that are a lot more than this, then it takes more steps to solve. So we don't want to trace back, we don't want to just keep looking over and over the steps. Sometimes, no matter how many times we look over the steps, we're just not going to recognize the error. Okay, so we need to do the following. So the technique I've just shown in example 4 now is a perfect place to check whether we have arrived at whether we have calculated the correct, or whether we have derived the correct inverse function. Okay, and so now here's how we can check our work. So think of that example 2 that we were doing. So I did not do this when I finished each problem in example 2, but this should have been done. but we didn't learn this technique at that time. So now it's an effective way of doing this. You see, our beginning function was f of x equals 2x plus 7. Let's now think about substituting in this, what we believe to be, the inverse of f. So I'm going to do f of f inverse. Okay, and then so the answer will come out immediately. We have 2 times the inputs, but the input is right now x plus 7 over 2 plus 7. All right, the 2 cancel with the 2. Things seems okay so far, ending up with x plus 7 plus 7. And then now combining like term, we're ending up with combining like terms here, we're ending up with x plus 14. But we didn't end up with, and this is about the most simplified already, and we did not end up with x. This is a perfect sign saying that somewhere along our deriving work, we made errors, okay, in our work calculating the inverse of our beginning function here. So that brings a good sign for us to come back and trace our work right there. Otherwise, if that worked out just fine, it gave us an x, then we didn't need to go back and check every steps twice or triple times or anything like that. All right, so that's the usefulness of this kind of problems in example 4 that we just now finished, and we have done a few. All right.